Start my stream here, back onto the YouTube. So those of you who have had my classes before, well, this will be familiar. For those of you who haven't, welcome to the fun that is homework. So once you click on the homework link on the main web page here, it's going to ask for your last name, and it does not have to be case specific, but it does have to be exact with respect to what it says for you in Maui. Meaning if you have two last names with a space, that's what you type. If you have two last names with a hyphen, that's what you type, and it should match. If you can't get in, it's probably some difference in how you think your name is versus how Maui thinks your name is. If so, please email me and tell me what you think your name is, and I will correct it in my records. But the 8-digit ID is just your ID number from the University of Iowa. I don't have mine memorized, but it should be on your ID card or available to you otherwise. I'm actually going to sign in with one of my dummy logins that hasn't been used yet. All right, once you log in, you'll see this landing page here. This will have all of the homeworks that you have either completed or are still available throughout the semester. You'll note the due date for everything to be finished is here. This will let you know at any point in time how many homework points you have accumulated out of however many possible. Every time a homework closes, I have to manually download the homework data sets, make sure everything is cool, and then I'll upload the new point totals within a day or two. It'll also keep track of your quiz points, formative assessment points, as well as bonus points and things like that. So if we have homework 0 here, we'll begin or continue. Here we go. So there are 3 things to know. First is up here, there will be things to download. Every assignment after this will feature an individual specific data set, as well as syntax files in SAS or Stata to help you get started with your homework. So they will help you to import the data set. They will identify what the names of the variables are and give them labels so you know what they mean. That way you can just focus on the modeling and not fighting with software. Most of you, I think, have used the virtual desktop before. If you haven't, on my other class, I think, did I put that here? No, I didn't. I think I'm losing my mind because I was like, did I do this or did I not do this? For my other class, I actually have a guide to help you get started. If anyone needs that, it's under 6242. So if I go back to my course directory, 6242 is the class that happens right before this one. I gave them something called an at-home checklist for getting the University of Iowa virtual desktop to work. It turns out to be more complicated than you would think because you have to be running a VPN if you are off campus or connected to EduRoam if you are on campus. You have to have mapped your H drive to your computer, and then for this class I have example files for them, and then it has a series of steps. If you are somebody who has pledged allegiance to Stata and wants to be able to use Stata off campus and is willing to throw money at the problem, I will note that 6-month student licenses for Stata are $48, and here's the link to buy that. So if you're somebody who knows that you're going to need to use Stata and you're going to need it off campus, this may be an answer that you want to consider. I also learned something new about what is on campus. On campus means EduRoam. So for instance, there is a Papa John's School of Business something or another in Des Moines. That is on campus. So you can use Stata from there. So I imagine that any place that is a campus place that is not physically here, that is connected to campus, you should still be able to use Stata on as well. So, all right, where were we? Homework questions. 2 kinds of questions. Computational questions in which there is an exact right answer. I will let you know the precision to which you have to enter it. It's 0.01 in most of my assignments, but that won't be relevant for us today. So first question here, just to give this a shot. How many homeworks are planned? 6, and I'm really hoping to get through all of them. I've got a plan for this. And I hit enter, and it turns green. How many points total are the homeworks worth? 86. It's an arbitrary number, but it's because 100 minus 14 is 86. That's why, 68. So let's see what happens if I get it wrong. If I say 84, I hit enter, and it goes red. You have as many chances as you need to enter something else and have it turn green. I do not know how many tries it took, so there's no shame that's being tracked in terms of how many tries it took to get a correct answer. That's a frequent question. If you find yourself using this strategy, I'm just going to start plugging in every number on here until it works. That's a sign that you need to stop and ask for help. Because plugging in every number until it works may work sometimes, but it won't help you learn whatever it is that isn't working for you. Per my usual, how many points do you lose if you complete this homework even a minute late? 3. Do I do that to be mean? Why do I do that? Deadlines get shit done, that's why. With the best of intentions, without deadlines, things get pushed. So yeah, I want to keep this class a priority. But if you need to change a deadline because of something else and you're planful about it 2 weeks in advance, email me, let me know what you need, and I will be happy to work with you. But how many points are you getting right now for doing this homework 0? 3. So it's either 3 points extra credit or a free late homework, however you want to look at it. The other questions are these kind, results questions. So these you will not get to see if you're right immediately. You will get to find out if you're right after you submit it, but we'll practice here. So I am Lisa Hoffman, and by the way, it is just regular Lisa. It's not Lessa or Lisa or any other permutation. Have I told you guys the story of my name, where it came from? A few people? So the story of my name, my mom said that when I was born, I looked like a Lisa, but not the regular kind. That's what she told me. The regular kind being Lisa, which is the rest of the world. So I think there may have been some drugs involved because my mom is not normally that creative. But I'm happy with it because then I own the Google, as I said. So that's me. I'm Lisa. My office, where is it? South, which means just regular 356 without any number or any letters, right? Because it would be too much to actually label it. My office hours. Come and go, Chipotle. In or around this room or on the lawn. What do we think? Yeah, and I say or around because I may get kicked out with no notice. Office hours are not a priority for this classroom, so if somebody else needs the room, they kick me out. If that were to happen, I'll just hang out there where there's computers. I would like to come and go would be nice because depending on the time of day, you can get your coffee there, or you can get your soda there, or your beer there on the way home, right? It's like one-stop shopping, but they don't have tables. Chipotle has tables, but they're the most uncomfortable tables in the history of the world, and it's usually really loud. They do not want you to loiter at the Chipotle, as I'm fond of calling it. So yeah, we'll pick that one. My office hours are when? After this class, for both of my classes, until 4:30 this year on Tuesdays and Thursdays. If no one is here, what am I going to do? No. Here's my plan. Like weeks like this, no one wants to come to office hours. I'll probably hang out for like a half hour in this room and check email and just like make sure no one's coming. And then I'll go back to my office and I'll do the rest of my work. I will try not to leave early without letting you know unless there's an emergency or it's snowing or something like that. So you should be able to find me in either of those two places. All right, section 2, how many points do you get from participating in out-of-class assessments, formative assessments? That's the 14. By the way, if we end up having to drop a homework or a formative assessment because of time, I will just eat those points and you'll have a new possible total. So like if we only have 85 points by the end of the semester, your grade will be out of 85 points. I won't try to like recalibrate anything, it'll just be proportion earned. So that's 14. How many days are you supposed to be here? 2. Yeah, well, 2 days of classes. The reason for that, can you imagine learning stats for like 3 hours in a row? It hurts. It hurts me. Not just me, but it hurts you guys too. So I try to break it up a little bit so we can be a little bit fresher and have the stuff happen more frequently. And how many classes are we scheduled to meet by Zoom? Yes. Don't you guys know what Zoom is? It's like the newest thing.
I didn't read it by Zoom.
Yeah, I saw that earlier, and I was like, yeah, that's a good one. I'll just pretend that's a new app. But how many are we maybe meeting by Zoom only? There is 2. I don't know what's going to happen on those days because it depends on whether I'm actually kicked out of this room, whether they can find me another room. And I know that worst case scenario, we can meet by Zoom because I've done it before. So I will let you know ahead of time what we're actually going to do. Next up, SAS is currently available anywhere or only on campus? Oh, SAS is the one we're talking about now. SAS is anywhere. Stata it's only on campus, which is Eduroam. The hack to that, by the way, is if you use remote desktop to connect to a computer that is on campus and you run Stata from inside your campus computer, then it is on campus and you can do it from anywhere. And then last but not least, this class will be a cakewalk, a nightmare, or challenging, but in a good way. That's my hope. To me, that is the correct answer. So once you have all of your computational questions correct, it will say that, but it's reminding you that even though it looks like you're done, you're not really done. So when you're finished working either period or for the day, you want to make sure you hit this box for check and save your answers. If you need to pick up where you left off, then all of your choices for the drop downs should reappear when you log back in. So you do not have to complete this in one shot. Once you've decided that you're happy with everything that you've said, you can click on submit, but you're not done yet. So there's at least one person who forgets this every semester. I'm hoping that this will be the first semester, but we haven't. So once you hit that, you'll see that the drop-down menus go away and all of your answers are just straight text. That might make it easier to proofread or otherwise check that they make sense. And then you have 2 choices. Either you've decided you're happy, in which case I'm asking for your 8-digit ID code as your password to confirm that you want to submit. If you're unhappy and you want to go back, there's a button to do that. So I'm happy, 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to submit for real. You should get a message at the bottom telling you that you have been submitted, as well as what the due date is so that you can check after the due date to see what happened. My due date, since this is a dummy login, is different than yours. So I'll show you what it looks like after the due date. You'll be able to see view submitted answers, and then within the results sections, anything that is correct will be green, anything that is incorrect will be red, and the green correct answer will appear next to it. So that way you can see what you should have done. In terms of strategy, these homeworks will have lots and lots of questions. Each question then is only worth a very small fraction of a point. So if you find yourself working on this and it gets to be the 11th hour and you're missing 1 or 2 questions, it's probably a better deal to submit and miss those 2 questions and not take the 3-point hit. So anything that you leave blank, for the numbers, for instance, it will give you what the right answer would have been so that you can work on it later and try to figure out where you went wrong. And I'm very happy to help you in office hours to do that. Okay, bye-bye, Zoom. No one wants to talk to me. That's fine. All right. Questions? Okay, just make sure, that you hit the real submit, because otherwise it doesn't go through. If you're not sure if you've submitted, check the bottom here. It should be able to tell you what your status is. Okay, so that's that. Please email me if you are unable to access this. Otherwise, finish it please by Monday night. That way I can troubleshoot any other issues and we'll be on our way to the first homework, which doesn't happen until, let me go back, week 4, I think. Yeah, here it is. Yeah, I posted the checklist for the thing on here. I knew I put it somewhere. Couldn't remember where. So yeah, the 10th of February is when the first homework is due. So we got a ways to make sure that everything is working. Okay. Good? Okay. All right. Excellent. Now, let's see, we were in lecture 0 last time, and I managed to horribly embarrass myself because I couldn't come up with the right coding for a 3x3 design off the top of my head. So I fixed it. I spent a couple hours yesterday making up a new example by which to redeem myself. And I emailed it to you, and it's right here. So please grab that along with lecture 0 so that we can talk about those things. So we'll pick up there, do a little bit of reviewing, and then move on. So what I'm trying to do here is give you my big picture of why I put the stuff in the class, why I put it in the way I did, and what it's supposed to help you with. So I'm trying to build you towards your future with further models or to help you better understand the models that you already know. So in my worldview, there's only 4 things that go into a really deep knowledge of quantitative methods. An understanding of linear models, which is what we're reviewing right now, an understanding, at least at a basic level, of different methods of estimation. Now, I'm not talking like knowing how to write algorithms level of estimation, right? I'm just talking conceptual. Understanding why sometimes the answers come quickly and sometimes they come more slowly. Or why you are taught that you can or can't do certain things is often tied to what the rules of estimation are. Link functions is what we're picking up in this course, which is the means by which we can predict any kind of outcome, not just those that are supposed to be normally distributed. And understanding these 3 things are going to help you pick up the 4th Lego block, which is the addition of random effects or latent variables. And so this happens in multi-level or mixed effects models as they're known. This happens in confirmatory factor analysis, item response models, which is confirmatory factor analysis with link functions, and SEM, which is all of the above. And I am teaching that class in the fall. So any of you who are planning to take that, it's really good that you're here. If you know anybody who might want to take that class in the fall, tell them to come. I don't care if they register or not, but hearing the material would be really useful, I think. I'll tell you some stories about that because I learned this stuff backwards. So that's how I'm coming at it from my perspective. So we started talking about linear models, the idea of how you enter predictors into a model to be able to answer questions about the effects of those predictors, and how to make sure that you are using the right terminology and interpretations for what the numbers mean that come back. That's the idea of linear models. So when you only have, say, this is slide 12, one example of one predictor, it's pretty straightforward. So if I have education predicting income in this model, this would be called a simple linear regression because education is a quantitative variable. I know that the effect of education is bivariate, meaning it's not controlling for anything else, and because there's nothing else in the model, it's marginal. Beta 1, this slope, is the expected difference in y per year of education for everybody. That's what marginal means to me. When we start adding predictors, it gets a little more tricky. So we were talking about the different kinds of effects this time. So fixed effects is sort of like the broadest term. Fixed effects, by definition, are effects that are constants in a model equation. In other classes, that's contrasted with random effects, which become variables instead. But in this class, it's fixed effects. They can either be an intercept. So in most cases, there's one intercept in a model, but that's not necessarily true. So the thing that I built you that I want to go over today gives you your first example of when that might not be true. Otherwise, it's a slope. All slopes are the same. It's the change in y per unit change in x, or as I call it, difference, to be a little bit more specific because change refers to longitudinal in my head. Slopes can be one of 3 kinds. They're either bivariate or unique, where bivariate means that it's a slope by itself, not controlling for anything else. Unique means it's controlling for all the other predictors in the model. And then there's the marginal versus conditional. Marginal means that slope is the effect of the variable, period. Conditional means it's the effect of the variable conditioning at the 0 value of an interacting variable. And so this is where we left off last time, practicing labeling these fixed effects. So here's an example equation. I'm just coming up with letters. I didn't pick A, B, and C because B and beta look a lot alike, and I thought that would be confusing. But it doesn't matter what kind of variables these are. These could be dummy codes, these could be quantitative predictors, they could be linear and quadratic terms, doesn't matter. All of it works the same way. That's what I mean by a linear model's worldview. So we did last time the effect of f, I'm calling it unique marginal. Everything in terms of the slopes on this page is unique because it's controlling for the other stuff. It's trying to give the contribution of that predictor factoring out the relationship with all of the other predictors. The question is that whether or not we can say beta 1 is the effect of f period, or is it only the effect of f for certain kinds of people? Period is marginal, certain kinds of people is conditional. In this model, f only shows up in one place. That means f has a slope that is marginal. Beta 1 is the change in y per unit change in f for everybody. Then we did g. G shows up in two places. That means automatically it's conditional. In order to know how to interpret beta 2, we have to know when h is 0. When h is 0 is a decision you get to make. There is no wrong way to center a predictor, only ways that are weird. You can leave it uncentered, and then the effect of g, beta 2, would be specific to h is 0. Maybe 0 is a meaningful value, and that's fine. Maybe 0 is impossible, and then it gets weird. But we learned last time how to find, via this linear combination, what the model says the effect of g should be for any kind of person. At a minimum, it's beta 2. It's only beta 2 when h is 0 and this part cancels. It becomes beta 2 plus beta 4 times whatever value of h you're talking about. So the reason that I think this is so important is that too many people don't understand this conditionality, and they start making broader conclusions about the effect beta 2 than they should. So beta 2 is known as a simple slope or a simple effect. Simple means conditional. I think that term is sort of funny because like simple is a like, oh, it's this, it's so simple, right? And it's not. That's just what they call it. But it's really tempting to look at, say, the coefficient that shows up for beta 2 and be like, oh, g doesn't matter, or g is significant. But that number is only one of an infinite number of possible numbers that could describe the effect of g. It's not enough information. And if you don't know how to ask for these kinds of linear combinations, the only way that you could get another version of the g slope is to change how h is coded and rerun the model. That is possible, but it's a pain in your ass, and you don't need to do it that way. So knowing how to ask for these things is really helpful. And that's what happens via estimate statements in SAS, lincom in Stata, test in SPSS, as well as new and model constraint in M+. I always forget what it's called in R, but it has it too. I don't remember. But this, yeah, R people are in this class, right? Yeah, there are some R people. So you should know, right? No? I don't remember what it's called. I know it exists. Let's put it that way. But every package has a capacity to do this. So to be able to get the information that you specifically need to address your question is really helpful. So then we're ready for H, right? So the effect of H, which kind is it? Also unique conditional. All right. Now how do I get its effect? Step 1, find the H's. Step 2, factor out H because that's the thing that I'm trying to find the slope for. So what I'm trying to find is the term that will multiply H in the equation. And it doesn't seem to want me to delete only the H in this case. There. Stop it. Nope. Fighting with the PowerPoint. Okay, all right, you can have your extra parenthesis. I give up. But now beta 3, that's the effect of H specifically when G is 0. It's only one of an infinite number of possible H slopes. You can get a different one depending on what value of G you have. So if G is a grouping variable, say it's a binary variable 0 or 1, then this gets easy. You could find the H slope for people who have G0 and the H slope for people who have G1, and you're done. If G is a quantitative variable, there's a whole bunch of possible values. Something that I would recommend in that case is something called regions of significance. You guys may have heard me talk about this before. I don't think we'll have time to do it in this review. Actually, I know we won't, but I can point you towards examples that I have. Basically, you would try to find the levels of G at which the H slope shuts off and turns on in terms of significance. Because there's some range at which it's going to be negative, some range in which it's 0, and some range in which it's positive. And you can reverse engineer the t-test for the significance of the slope to find that out. And so those things can be useful to report in a situation where you want to know over what range of G values you need to worry about the effect of H. Okay. I'm talking fast again, so I'm going to stop, sip my water, and ask if you have questions. No? Okay, well, thank you for shaking your head. That makes it less ambiguous, right? Because I'm lost and move on, I'm bored. Those faces are the same from where I'm standing. So I don't know which it is. We're good? Yeah, okay, 2 thumbs up, she says. All right. Then we're good. So a linear model's worldview. The things that you know all fall under this one umbrella. So unlike the rest of statistics, this is the only place it happens. Special names for different kinds of predictors. Only in general linear models does this happen. These distinctions die after today. So if you have you're predicting a continuous outcome whose residuals are supposed to be normally distributed. If you only have one quantitative predictor that is simple, meaning not simple as in simple slope, but simple as in only one, linear regression. And the linear, by the way, is to differentiate it from other kinds of regression that we're going to learn in this class, like logistic or count or other stuff like that. If you have more than one quantitative predictor, then it switches to multiple as opposed to simple regression. If you have one categorical predictor with only 2 groups, that is known as an independent or 2-sample t-test. If you have 3+ groups for your categorical predictor, and there's only one predictor though, that's called a one-way ANOVA, or analysis of variance. If you have 2 or more categorical predictors and likely an interaction between them, which is a software default, you have a 2-way ANOVA. And if you throw in a categorical predictor, but you don't let it interact with your, you throw in a quantitative predictor, you don't let it interact with your categorical predictors, then it becomes analysis of covariance of whatever way. So all of these words refer to different flavors of predictor models, but it's all one thing. And it drives me nuts when people try to talk about them as if they're different, because it just makes it harder than it needs to be. So this is the perspective that I'm starting from. We're going to work with models that have different types of outcomes from the same perspective. I'm not going to use special names based on what combination of predictor variables are in there, unless it serves to help explain to people who are familiar with these terms how they relate to what they know. The reason why I say these are all the same thing is because they are all based on this thing right here, E sub I. E for error or E for residual, take your pick. All of those models on the previous page say that E, for each person, the collection of E's from your sample is supposed to have a conditional normal distribution. Conditional in this case means normal after the predictors. It doesn't mean it has to start out that way. So this is one of the biggest problems you'll see in some textbooks where they put chapter 2 as things like outlier detection and data cleaning. You heard these terms? When you hear that, go, blah, 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 stop talking. Because you can't do those things outside the context of a model. Because what Y looks like may not have anything to do with what E looks like by the time you're done with it. So detecting leverage points and outliers and whether or not normality has been obeyed only happens to the E's, and you don't know what the E's are until you're done modeling. So that's one thing. So you will see this idea written like this, where Y sub I, the outcome, is normally distributed, and then it refers to the parameters of the normal distribution. Mean is always first, but it's conditional mean. Rather than saying it's the mean of the overall variable, it's the conditional mean that's given by the linear model equation. So it's still a mean in the sense that anybody who has the same combination of predictor values would get the same score. It's just conditioned on x1 being this and x2 being that and x whatever. The second place is either a standard deviation or a variance, depending on who you read. Standard deviation squared is variance, but it's the variance of the residuals. And so that's the conditional normal part. It's the E part. Now, in some of the models that we're going to learn this semester, there is no residual variance. It's gone. It's not that the model's perfect. It's that it doesn't get estimated as a separate parameter because it is determined by the mean. So this is different from now on. We have to pay attention to whether or not there's a variance there. Another thing that you are told, the E residuals are supposed to be independent. What's the difference between an independent residual and a dependent residual, folks? Let's review. I just talked about this in my earlier class today. Can you give me an example of when this would not be true, that they're independent? I know you can. Multi-level playful. When it's clustered, like what does that mean?
Like if you have students in classrooms, the residuals among those students are going to be more alike than different classrooms.
The students from the same grouping,
Yeah.
classroom or teacher or whatever, are going to likely be more alike than students from different. Yep. I'll keep the focus on you since you mentioned this last time. What about family data, where you have answers from siblings and parents and things like that?
Those will also probably be more alike. They share the same environment and they interact with one another.
Yeah. So residuals from people from the same group of some kind, family being one example, romantic relationships, all kinds of different dyadic data have the same problem. Let's say if you measure somebody repeatedly, like a longitudinal study, the E's from the same person are more alike than E's from different people. What if you measure people repeatedly across the same items? Like everybody answers the same 40 questions. Dependent. E's that go with the same item and that go with the same person are going to be related. So it's actually pretty rare in real world data that this would be true. What if it's not true? Then what? Pack up and go home?
Can't you specify?
Yeah, you add something to the model that fixes the problem, meaning you need to go get a new model. It doesn't work anymore for you. It's not the end of the series of choices. Briefly, the way that you fix it is to tell the model to be able to have more than one kind of E. In the last example, the same people answer the same 40 questions. There's a person E. Why are some people better at this test than other people? There's an item E. Why are some of these items harder than other items? And then there's an E for the combination. Why did this person, who's usually smart, do so bad on this item that's not that hard? We call that residual. In the case of cluster data, We would have student E's, classroom E's, except they're called U's. But yeah, you change the model to fix this. That's one thing. The other thing that goes along with this, besides normal independent, is constant variance. This model, written right here, y sub I is normally distributed with a mean of y hat. Y hat has an I subscript. That means each person gets a different y hat potentially, right? But everybody shares the same E variance. That doesn't have a subscript of I on it. Could it? It actually could. So this idea of constant variance more specifically means only one variance that's shared. Otherwise said, the model predicts equally well for all people. So that idea goes with this picture, which I stole from somewhere. If you have a regression line that looks like this, the most likely value for a person's data is right on the line, and how far off you are from the line is conveyed by these happy little bell-shaped distributions, conveying the normal, but they're all equally wide. So the regression line works equally well as you go up X. In contrast, you might have something like this. So I stole this picture. The labels were already there, which I think I liked. Here's an example of constant variance, right? Flat and even. Here's an example of non-constant variance, which is heteroskedasticity. How many syllables is that? That's a lot of syllables for non-constant variance. But it's not good from the perspective of it doesn't match the model we picked. But that just may be what happens, especially for things that have natural boundaries. Like if you're predicting a count of something where the lowest you can be is 0, like you can't wiggle around 0 as much as you could potentially wiggle around like 1,000,000, right? Like the higher the value, the more likely there's variability around it. So some of the models that we're going to look at build in specifically this type of pattern where the higher the mean, the higher the variance. Because that happens in real data, but that's not the GLM. Okay, so the thing I wanted to show you, see, this is an example of why it's good to come to class, because I made up this thing off the top of my head. I predictably screwed it up. I felt bad about it, and then I went and fixed it. So I'm trying to redeem myself here. So this is the thing I sent you via email and is posted on the webpage. I put it up as a Word document so that we could manipulate it more easily together. So this is a two-way ANOVA. I'm going to show you 2 different ways that you could set it up. What is actually happening behind the scenes in terms of how this model is actually regression, how it is a linear model. So there are, I'm calling 1 dimension letter and 1 dimension number. And so there are 9 unique possible values that show up from the crossing of these things. Most questions from this type of design is basically, are these really 9 unique things, or are some of these basically the same? Another type of question is, are the differences along one dimension constant across the other dimension? So let's say that we know that treatment C works better than treatment B, which in turn works better than doing nothing, which is A. And let's say that 1 is a certain type of person, 2 is another kind of person, and 3 is a third. Well, we might want to know, is C always the best treatment? Even if it's person 2 or person 3? Is the difference between B and C equivalent as we move across people? Those are interaction kinds of hypotheses. It's moderation. Is C best? It depends on whether you're person 1, 2, or 3. So the same types of questions you'd want to know in any kind of regression type model just showing up as groups. So here's the traditional way that your software is going to help you do this. I'm showing you what's going on under the hood when you declare these variables as categorical and you throw them in a model. So here are the 9 types of categories, and I've created 2 variables that differentiate among the possible values for the letter variable, A versus B and A versus C. This is known as dummy coding. Based on the coding scheme, group A has a 0 in both. That's how I know they're the reference. So the title for these things is my way of saying what I intend for this variable to capture. I give the B people a 1 and the C's a 0. So if I only had this model, this variable in the model, it doesn't actually mean A versus B, does it? It means A and C lumped together versus B. Its bivariate effect would be A and C lumped together versus B. Likewise, this one lumps together A and B versus C. So these two terms work together. A and C are lumped together by the first contrast, but B is separate. Then the job of the second contrast is to go and differentiate the two that were lumped together. Same thing happens for setting 1 as the reference, and then separating out condition 2, and then the third one separates out 1 from 3. Okay, with me? This is not the only way to set this up, but this is probably the most common. So here's model 1. The reason that I knew that this was broken in class is because if I have the right model, I have 9 fixed effects in it because I have 9 mains. The model should be able to pull apart every single one of them. But the way that it does it is convoluted as hell. It's the opposite of good as hell. See, thank you. I was going for that Alyssa reference. Baby, how you feeling? I'm confused as hell. What's that? I'm going to ask for a theme song next week. Get ready for it. You can't pick the same one you did last time. I won't allow it. Yeah, I know. Yeah, I was listening to the radio on the way in. I'm already ready for this. I've got it. So here's my model. I have an intercept, beta 0. That is the you are here sign of the model. That's my reference point. Every other term is going to move me off of this cell in one direction or the other. No, because one direction or the other is like the way. No, I don't go there. No, I left boy bands after like New Kids, so yeah, I'm not going to weigh in on the NSYNC versus Backstreet debate. I'm just not. Although I am familiar with them. All right, here's the next two terms. These are main effects of letter, but because they also show up in later interactions, we know they're simple effects. So beta 1 is the difference between A and B for people who are in the 1 group. Likewise, beta 2 is the difference between A and C for people who are in the 1 group. Similarly, here are the contrasts that differentiate the numbers. Because of their interactions, it's the difference between 1 and 2 for people who are in the A group, and 1 and 3 for people who are in the A group. So out of all the possible differences I'd be interested in, I've only got 4 so far. That's what I got. Next comes the convoluted portion of the model. 4 interaction terms, because each of my simple main effects has to be multiplied by the other variables. And I know this is right because I'm up to beta 8. And that plus beta 0 gives me the 9. Now you may look at this and go, what the hell? Right? It's a little bit much to try and parse through. But the same ideas as if these were quantitative variables readily apply. So let's start with these two. Do you remember the 4 kinds of interactions in the world? More positive, less positive, more negative, less negative. That's it. So you would use one of those phrases depending on the direction of the coefficients. So let's say that beta 1 is positive. because B is supposed to be better than A. Let's say that beta 5 is positive. So we know that beta 1 is the difference between A and B for a 1 type of person. Beta 5 would tell us that the difference between A and B is more positive if you're a 2 kind of person. If beta 1 were positive, beta 5 were negative, then I would say that beta 5 says that the effect of A versus B is less positive or smaller if you're a 2 person. So the difference is not as impressive in 2 people. And the same thing would happen anytime that these signs are opposite, they're working against each other. That's a less something, meaning the effect has been weakened. If they're in the same direction, that's a more something, meaning the effect is stronger. I could also come at this the other way. Here's that as a starting point. Beta 3 tells me the difference between the 1 and 2 kind of people for group A. Beta 5 would say how that 1 to 2 difference is different in group B. So you could walk through each of these and figure out what they all mean, but you still wouldn't get all the information that you need, because there are several differences here that are implied by the model as linear combinations of these fixed effects that are not given to you. But in typical ANOVA output, even though this part, the betas, might be presented, it's typically not focused on. What you would get is a table of means, basically to fill in this, and that shows up in your results section. I'm not a fan of this, if you can't tell. I'm starting to get that sort of snarky, teachy thing I do. They would also give you a marginal F-test for the effective letter. So ANOVA software, when you ask for that, this is what you get by default, which means that it would give you a 2 degree of freedom F-test as to whether this set of 3 means is different. Note that that has nothing to do with our original question as to whether or not C is always better than B is better than A, because it averages across these people. It could be the case that in group 1, C sucks, and it's group 3 where C is awesome, right? We wouldn't know that if we average across the numbers to go to the margins. Likewise, we get an F-test for whether or not these 3 means are different from each other. That's another 2 degree of freedom with the same limitation. And then we get a degree of freedom equal for F-test for the interaction, meaning lumping all of these terms together, is there an interaction? Well, if the answer is no, you could probably go, okay, thank God, because I wouldn't know what to do with that. If the answer is yes, then it's like, okay, it interacts, and that's it. Then you look at your numbers and go, okay, it looks to me like this one's more bigger here than here. And people might be tempted to start carving up this table into little t-tests, but you can't do that. Do you know why? Error. Yeah, say that, say.
The alpha gets bigger? Error, though.
That wasn't where I thought you were going with it, but I'm going to put a pin in that one and come right back. But error something else. We go back to...
If you go to TTS, like you don't count like a total error.
Yeah.
Like 3 interactions.
Yeah, it's the error that comes from the model is this one, right? It's lumping across all 9 kinds of things, and it's coming up with what's known as a pooled error term. Now, if all 9 kinds of things mostly have the same error, that's cool. But if they don't, then that means rut-row-raggy. Some of the groups have more error, and that means their differences are not actually that big. So carving this up and doing little t-tests uses a different error term for each combination. So the results are logically inconsistent with the model if your model only has 1 error term. Now, would it be possible to allow each of these 9 groups to have a different residual variance? What do you think? Doesn't that seem like a thing we could do? I mean, we've gone to the moon. We have the internet. We have TikTok. I learned about today. Surely I can have 9 variances if I want, right? The answer is, sure you can, so long as you're willing to leave least squares land. Things where you're calculating sums of squares that lead to mean squares versus f, all of those things are only possible if you have the same variance throughout the whole thing. We got to leave least squares land to make it work. But if you were to allow all 9 cells to have a different variance, then in theory the separate little t-tests would be able to help you. But that just gives you the simple differences. It doesn't give you the difference of the differences, which is the interaction. So this degree of freedom for interaction term, some people say, because error, so I'm coming back, Terry, some people say is a logical prerequisite to going digging. Like once you have your significant interaction, you get to start like digging around to see what caused it, right? But there's a lot of possibilities in which you could have one of the interaction terms be significant, the other 3 not, and it washes out the omnibus test. So the traditional logic is this has to be significant first, otherwise alpha inflation, type 1 errors, and bad. Stop it. No. Here's my perspective. These interaction effects are the ones that would show up by default on your output. These are just the ones that happen to be there because of your coding. But all of the other ones are in your model. They are linear combinations of things you estimated. So I refuse to give special privilege to worrying about type 1 errors for certain kinds of results that are presented by default versus ones that you ask for. They're all in the model. And if you use p less than 0.05, 1 in 20 things that you're looking at is wrong. I just don't make the distinction between the kinds of things. Because if this were a regression model, where these are quantitative predictors, and you started working with simple slopes and stuff, no one would say a word about error inflation. It only shows up in these sorts of analysis of variance designs when you want to actually do your due diligence and figure out what the heck this actually means. So here's what it actually means. Here is how the model gets you what the mean is for each cell. If you work out the coding of zeros and ones to create an expected outcome for each type of person, this is what you're left with. So then it becomes a little easier if you start from here to figure out how to get all the answers to the questions that you might want to know. So for instance, is C better, or I'm going to start here, is A different than B? Well, if I start here, the difference between them is given by beta 1. I don't have to ask for that, it will show up. Likewise, the difference between A and C, nope, stop that. Come on, Word, you're making me angry. Okay, apparently it's going to make me really angry. Stop it. No. There, that looks a little better. And now you know why I always make tables in Excel and paste them into Word as objects, because it does this kind of thing to me. It makes me irrationally angry. And it won't even let me fix my 0. All right. Anywho, beta 0 versus beta 0 plus beta 2. You can tell beta 2 is the unique thing. And you could work that out for any simple combination, simple effect meaning just one difference like that. But then trying to figure out how the differences differ. So let's do this one versus this one. And now you also know why I use PDFs, right? Oh my goodness. I'm going to act like my husband now and start yelling about technology. He's not an angry person. He's actually pretty patient. But when bad drivers and programs that don't do what he wants them to, then he's like crazy. And now I'm channeling him today. Okay, there. Now quit messing with my subscripts. Okay. So what's the difference between these two cells? Beta 1. Okay. And what's the difference between these two cells? Beta 1 and beta 5. If I have beta 1 and then I compare beta 1 to beta 1 and beta 5, what's the difference? Just beta 5. So you can work through all the possible combinations that would answer the question, is B better than A to the same extent if you are person 1 as if you are person 2? And the answer to that question is beta 5. Is C better than A to the same extent if you are person 1 than if you are person 2? The answer to that question is beta 6. To get the ones that are not model-based parameters, the ones that are here, is C better than B to the same extent if you are 1 versus 2? Then you got to start lumping these things together. And as an exercise, I did this for you. So these are what's known as interaction contrasts. They are the difference of the difference. So I've written these in two different ways to convey that the same answer holds for two different kinds of questions, depending on which is the moderator. So this first question is phrased as, I care about the effective letter. And I want to know if the effective letter generalizes from person 1 to person 2. The answer is beta 5. No. Reviewer 3, on the other hand, they think that you should care about the effective number. And they want to know if the effective number generalizes from group A to group B. Dear Reviewer 3, thank you for your careful read of our manuscript. Fortunately, the answer to your question is already phrased as the difference of the difference, because the difference of the difference is the same as the difference of the difference. So which one is the effect and which one is the generalizer? It's all math. It doesn't care. Math don't care. Usually you have one way to pitch it that makes more sense. And so the ones that are directly provided by the model are the ones where they are relative to the reference cell. So cell A and 1. So A versus B and 1 versus 2, A versus C and 1 versus 2. The ones that move off the reference cell in one way are a linear combination of two different interactions. So the difference between beta 5 and beta 6 here, beta 7 and 8 here, and if they move off the reference cell both ways, off of A and off of 1, then the answer to this last question takes all 4 of them. Okay, so raise your hand if you're like, this is really complicated, I don't like it. It took me like 2 hours to do this and make sure it was right. Do you like? Can I get a hell yes? This is really complicated and I don't like it. What if I told you that if you understand how linear models work, I could make it easier for you? Yeah. Or easier in any case, but especially easier, what if you have a design that's not fully crossed? What if this cell was not logically possible, so you don't have it? So for instance, you might have something like no feedback, positive feedback, and negative feedback. How many different kinds of nothing can you have? Right? So you might end up with a design in that case where you have like one condition that's like nothing, and it's the same nothing here and here, right? But then you want to compare the one nothing to 6 other kinds of something. That could happen. Well, your SOL, for the youngins in here, that means shit out of luck. to use this sort of coding scheme, because this relies on all 9 to be there to make this work. But there's no law that says you have to rely on slopes. What if we said, nope, I'm just going to use intercepts? I'm going to make myself 9 dummy variables, a 1 if it's that cell, and a 0 if it's not. Now I got my 9 cells, or my 6 cells, or my 7 cells, or whatever. Now what's missing from this equation that's normally there? Beta 0. So what's special about this is that beta 0 is normally, if you think about dummy codes that have 0s and 1s, beta 0 is a column of 1s. It applies to everyone's score regardless of any variable. So it's like it's being multiplied by a column of 1s, and if you write this out using matrices, that's literally what happens. But all the betas here are attached to something. So these are what's known as like custom intercepts in my vocabulary. You can think of them as switches. If I'm on cell A1, that's the only time when this is 1, its mean is given by this. And everything else zeroes out. And then 9 more times that happens, or 8 more times. So you're not having any slopes. So then your task is to figure out which differences or differences of differences you want. And so here's the same thing done a little bit more simply. So if I want to know if the difference between A and B depends on 1 versus 2, then I have the difference between A and B for 2 relative to the difference between A and B for 1. The end. So the thing that this allows you to do is ask for differences that are not necessarily tied to dimensions. So like in this design, I might have a reason to ask if A1 is better than C3 to the extent that A2 is better than C1. Right? You could ask anything you want, and if you phrase it this way, you can get to it. So this type of coding scheme where you're just like, F it, I'm not having any slopes. That way I can control everything. I've written this in grant proposals to do what's known as SMART designs. Have you heard of these? It's a type of randomized trial where you stop it midstream and you see who is responding and who isn't. And the people who are not responding get reassigned to do something different with some probability so that there's more conditions at the end of it than you started with. It's a special case of a cell-like design where not all the cells are there. Because the people who initially started, who are responding, don't get a chance to be in one of the other like special situations. And so rather than trying to figure out all the slopes and all the possible interactions of the slopes that are logically possible, I just proposed a model that looks like this so that I can ask it for whatever I want that corresponds to the hypothesis. This, by the way, is the same rationale by which we will do multivariate models using univariate software. So predicting more than one outcome at a time by stacking them all into one column. So let me use Kelly. It's like I know your data, I don't remember your name. Let's say that you're predicting responses for mom, dad, and your kid, right? So it's like family is what you're analyzing. And so you would need a column that says, like this is kid response, mom response, dad response, like all stacked up in a row. That's why. These sorts of things right here, let me borrow this and steal it. Insert, come on. Insert a page break. Okay. We're going to do this semester. I'm just foreshadowing. Is that cool? This is why linear models run the world. So let's say that, let me fix these people. Kid. Forgive the subscripts because I'm trying to do this fast. I have an example that's like this, by the way. Because at Penn State, when I worked there, everyone had this kind of data. Okay?
The only other person that uses this data is someone at Penn State.
I was in their HDFS program, which at some places is behaviorist, but at this place was like super quantitative, and it was developmental psychologists, political science people, some sociology people. It was like this whole thing of people who did really heavy-duty quantitative methods. And it was really cool because they had lots of data to play with. Okay? So let's say that my objective is to predict responses for the family all at the same time. Okay? This gets me started. This would be an empty model. Empty model has no predictors, right? No slopes, 3 intercepts. So I've got a kid mean across all the kids, a mom one and a dad one. Now what if I wanted to know if, let's give me one of the traditional covariates, variables that someone else cares about who's not you. That's my definition of a covariate. Come back. There we go. Father's education. Do you think father's education affects kid whatever? Sure, right? Well, you better control for it or else. Father ed here. Can I just say fed? Can we work with that? I need a fed here. And I need a fed here. Now, why is it? Okay, anyway. So, now note that this model does not have a main effective fed. It only has what look like simple effects because they look like interaction terms, but they're not. They're nested effects. They're switches. So this beta, now I need new numbers. Gotta fix it, sorry. Can't have sloppy notation. That's another thing that makes my husband irrationally angry. Sloppy notation. Bad driver, sloppy notation, and technology that doesn't work. So beta 4 is the effect of father's education on kids. Beta 5 is the effect of father's education on moms. Beta 6 is the effect of father's education on dads. Now, what if I had a hypothesis that father's education was more impactful on moms than dads? Could I have that hypothesis? Sure. That would be the difference between beta 5 and beta 6. Done. So when we set up multivariate models, this multiple intercept strategy will allow us to write a separate regression model for each type of outcome to test whether or not their effects are the same, to include them if you don't need them. So let's say we ran this model and we found out that father's education didn't actually matter for the kid outcome. Okay, take it out. Leave it for the others for which it does matter. Yeah, question?
How about error term?
We're out of time already? How does this keep happening to me? Probably because I go off track. What about an error term? Yes, thank you, reviewer 3. Based on this, you have these responses and they're dependent. And what about the error term? Isn't that bad? No, what I haven't shown you is that I actually have 3 kinds of errors. I'm going to have an E for kids, an E for moms, and an E for dads. And I'm going to build in a special way to let them all be correlated. So the E from the same family get to be correlated, but the families are still independent. For those of you who've taken the longitudinal class, I'm talking about an unstructured R matrix. For those of you who haven't, it's okay. But how can I do all this cool shit? Foreshadowing. Because I'm leaving least squares land. because I'm switching from things we can calculate via sums of squares, which are only possible for very restrictive cases of independence, constant variance, and normal residuals, to switching to likelihood estimation. Then it's like if you can think it, you can do it. And the good news is that if you understand what this is, then you can do it. What is this? Tape measure. It's a ruler, right? Maximum likelihood tries to make the data that's as tall as it can be. Yeah. See, dot, 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 dot. That's where I'm going to leave off. To be continued. Yeah, the crossover into next week's class is going to explain how I can do all this cool shit. How about that? All right. Hooray. So go watch the crossover event. Have a good weekend. Otherwise, let me know if you need anything.